All right, today we are pulling back the curtain on the real magic inside your computer. We're talking about threads, the invisible, secret workers that make everything you do feel incredibly fast and seamless.
So you ever stop and think about it? How in the world can your computer juggle so many things at once? I mean, you've got music streaming, you're in the middle of a game, and bam, a notification pops up and nothing misses a beat. How is that even possible? Well, that's exactly the multitasking puzzle we're going to solve today.
Okay, so let's dive right in. To really get our heads around how your computer juggles all those tasks, we have to start with something called a process. And you know what? The best way to think about a process is to picture a restaurant.
See, every single application you run, your web browser, Spotify, a game, whatever, it gets its very own process. Just think of that process like a complete self-contained restaurant. It's got its own street address, its own kitchen, its own tables, basically everything it needs to operate, and it's totally separate from all the other restaurants running on your computer.
But here's the thing, a restaurant building itself doesn't actually do any work, right? You need people inside to cook the food, take the orders, and serve the customers. And this is where we meet the real stars of the show, the threads.
A thread is the actual unit of work. It's a single path of instructions that your CPU follows. So if the process is the restaurant, then the threads are the chefs, the waiters, the dishwashers, you get the idea. They're the ones actually doing stuff. A single process might have just one lonely worker, or it could have a whole bustling team of them working together.
All right, so to make this crystal clear, let's put it side by side. On one hand, you've got the process, our restaurant. It's this big, self-contained building with all its own resources. And on the other hand, you have the threads, the workers. They're the individual task doers who live inside that restaurant and share its kitchen. Getting this distinction is absolutely key.
And here's where it gets really interesting. Look at that left column, the shared kitchen. This is stuff all the workers, all the threads, share. They have the same recipes, the same ingredients, the same ovens. But then look to the right, a worker's private clipboard. This is what each thread gets for itself. Every single worker has their own ID, their own set of tools, and their own personal to-do list, which in the computer world we call a stack.
So you might be asking, why even bother with this whole model of restaurants and workers? Well, it's because using threads is an absolute game changer for performance and efficiency. Let's break down exactly why this is so powerful.
It really all boils down to three huge wins. First, threads let you squeeze every last drop of performance out of your hardware. Second, they make it super easy for different parts of a program to work together. And third, they're just way more efficient to manage.
Let's start with maximizing your CPU. So modern processors have multiple cores, right? Think of those as individual kitchens. If you only have one thread, you're only using one kitchen, no matter how many you have available. That's a waste. By using multiple threads, a program can run tasks on all the available cores at the same time. It's literally like hiring more chefs to cook more meals at once. This is how you get true parallel power.
Next up, sharing. Because all the threads are working in the same kitchen, they can pass information back and forth instantly. I mean, trying to get two separate restaurants to share ingredients. What a logistical nightmare, right? But with threads, it's as simple as one chef putting an ingredient on the counter for another one to just grab. It's direct and crazy fast.
And finally, efficiency. Starting a brand new process is a heavyweight operation. The operating system has to set up a totally new, isolated space for it. It's like building an entire restaurant from the ground up every single time. But creating a thread, that's lightweight. It's fast. You're just hiring a new worker to join the team you already have. The difference in overhead is just massive.
Okay, so the theory is great and all, but how does this stuff actually look in the wild? Let's check out a few of the most common ways developers put these workers to use in real-world software.
So, the simplest pattern is what we call the single task thread. You have one very specific, temporary job to do, maybe saving a big file in the background so your app doesn't freeze. You just spin up a new thread for that one job. When the file is saved, the thread's work is done, and it just, poof, goes away. Simple, focused, and super effective.
Now, a more advanced model is using worker threads. This is where you create threads that are specialists. You might have one thread whose entire job is just to listen for your mouse clicks and keyboard presses. You could have another thread that's dedicated to handling all the communication over the internet. Each worker has a specific, ongoing role, just like having a head chef and a dedicated pastry chef in the kitchen.
And that brings us to probably the most common and efficient model out there, especially for things like web servers, the thread pool. See, instead of creating a new thread every single time a task comes in, you create a whole team of worker threads ahead of time. They just sit there ready and waiting for work. When a new request comes in, it gets handed off to the next available thread. This is brilliant because it avoids the constant cost of creating and destroying threads, making the whole system incredibly responsive.
All right, for our last section, we're going to get a little more technical, but stick with me because this is a really important distinction. The big question is, who's actually in charge of managing all these workers? Is it the application itself, or is it the computer's main boss, the operating system?
So there are two main styles here. On the left, you've got user threads. You could think of this as the DIY approach. A library inside your application manages everything. And the key thing here is that the operating system is totally clueless. It has no idea there are individual workers inside. It just sees one big process. But on the right, you have kernel threads, where the OS is the manager. It sees and controls every single worker directly, handling all the scheduling for you.
Now that DIY approach, it's got some serious pros. User threads are incredibly fast and cheap to create because you don't have to bother the OS at all. But there are two massive cons. First, since the OS only sees one single process, it can't schedule your threads on multiple CPU cores. You lose all that parallel power. And second, and this one is the real killer, if one of your user threads gets stuck waiting for something, like a file from the hard drive, the entire process grinds to a halt. All your other threads get blocked right along with it. Ouch!
So, to get the best of both worlds, programmers came up with some clever hybrid models. The most straightforward is one-to-one, where every worker you create is a direct employee of the OS. The N-to-one model is that DIY approach we just saw. The OS only sees one contractor. But the really smart one is N-to-M. It's this flexible staffing model that tries to balance the DIY freedom and speed of user threads with the raw power and intelligence of OS management.
So let's bring this all home. The single most important thing to remember is this. Threads are the invisible workers inside every application. They are the secret sauce that lets our computers leverage all those CPU cores, and they are what create that seamless, responsive, multitasking experience that we all just take for granted every single day.
When you get right down to it, it's this simple. From a single process, our restaurant, comes a team of threads all working together in harmony to power every single click, every stream, and every notification on your screen.
And that leaves us with a really fascinating question to think about. We're moving into an era where our computers are going to have not just a dozen, but maybe hundreds of cores. The old ways of thinking about threads might not be enough. So what comes next? What's the next chapter in this story of concurrency? Well, that's the challenge for the next generation of computer scientists to figure out. Thanks so much for tuning in.